Okay, so in this mini lecture, we'll be focusing on the controls on subduction plate speeds and relatedly how things like convergence rate and plate age are used to classify different subduction zones and predict their tectonic expressions and behaviors. So it's helpful to approach the problem of subduction plate velocities conceptually as an energy balance. The main process that drives subduction and produces convergence is slab sinking, which we can think of as a potential energy of the subducting slab due to its negative buoyancy. And this potential energy will depend on both the density of the slab, which you've already learned is dependent on its age, and the length of the slab that is sinking. But if subduction plate velocities were a simple function of the potential energy of the slab only, then we'd expect to see a linear relationship between convergence velocity and plate age, with older plates sinking much faster than younger plates. This is what I've plotted on the lower left here. Plate age is on the y-axis, convergence velocity on the x-axis. And as you can see, there isn't a clear relationship appearing. And this is because there are several additional factors that actually counteract the potential energy of the slab and act to slow subduction rates. We can divide these into three general categories. Subduction is resisted by dissipation of energy into, firstly, the interface between the slab and the upper plate. You can imagine that where the slab is sliding past the upper plate lithosphere, there's frictional and/or viscous resistance between the two relatively rigid plates. And then secondly, there's dissipation into slab bending as it rolls over and attempts to subduct. The tighter the curvature is, the more energy that's actually lost in the bending process. And lastly, there's also energy dissipated around the slab into the surrounding convecting mantle. In other words, the mantle material within the arc of the slab and around the tip of the slab needs to be displaced somewhere as subduction gets going. So some of the potential energy of the slab is also dissipated there. There's a nice paper from the late 90s by Conrad and Hager that looked at this question of controls on subduction velocities and came up with this semi-empirical formulation that expresses this energy balance. This equation relates the plate velocity, Vp, to these potential energy sources and sinks. So in this equation, there are several empirical constants. Those are labeled as C, but the rest of the equation includes physical parameters that you will likely recognize, and I think you'll find as we go through them, they're fairly intuitive. So if we look first at the potential energy of the slab, this includes, of course, the slab density, rho, the acceleration of gravity, g, and this term alpha times delta T, where T is temperature. This term is just the heat flux, which you saw before as Fourier's law in one of Sean's early lectures. So this is the thermal conductivity here shown as alpha rather than kappa, times the temperature gradient within the subducting slab as a function of depth. And then also it's also important is the length of the slab and the thickness of the slab. So that's the term in this equation that represents the slab potential energy, and if taken alone, it would determine the slab sinking velocity. You'd have that linear relationship between Vp and slab sinking. But then if we move to the resisting energy sinks or dissipation sources, shear resistance on the interface will depend on the shear stress magnitude, tau, or it can also be written as viscosity if the rocks are deforming by viscous mechanisms. And it also depends on the length of the interface plate boundary itself, which it will in turn depend on the dip of the slab and the thickness of the upper plate lithosphere. And then dissipation into the convecting mantle will depend firstly on the viscosity of the mantle. If the mantle surrounding the slab is very weak, for example, then it will move out of the way of the slab quite easily, and therefore it'll hardly impart much resistance to subduction, whereas the opposite will occur if that viscosity is large. Also important in this term is A, which is the area of the convection cell, so an estimate of how much mantle is actually being affected by the slab subduction itself. And then finally, if we consider dissipation into the slab due to bending, we find it depends firstly on the slab viscosity. So again, you can imagine if the slab is very strong, it will be harder to bend, so lots of energy will be lost in bending it. Also important is the thickness of the slab. Here it's labeled HL, but actually it's the same as HS, just a typo there. And this should also be important because thin beams are much easier to bend than thick ones. And finally, as I mentioned before, the radius of curvature of the slab is also important. The tighter the slab is bent, the more resistance it will impart. So this kind of formulation is really handy for getting a rough idea of how fast convergence rates should proceed as a function of these very classic input parameters. So just to give you an example of an interesting relationship that shows up when you do these calculations and attempt to assess the role or the relative importance of the slab upper plate interface itself. The left-hand diagram is showing the viscosity of different subduction input materials for a given temperature range. These are curves that are derived entirely from rock deformation experiments. And I don't want you to worry about the details of them individually, but what I do want to highlight is simply the difference in viscosity over the shown temperature range for mafic rocks, labeled here as metabasalts, versus sedimentary protolith, labeled here as metasediments. You can see from this plot that metasediments are all an order of magnitude lower viscosity than the reference mantle, whereas by contrast, metabasalts are 1 to 3 orders of magnitude higher viscosity than the reference mantle. So then on the right-hand diagram, we tried to use this information to assess what influence this viscosity contrast between sediments and mafic rocks might have on plate velocities using the formulation I showed you on the last slide. And what's interesting about this is that the interface material does actually matter for plate velocities. So on that right-hand diagram, plate velocity is on the y-axis, interface shear zone viscosity relative to the mantle is on the x-axis. And you can see that sediments are so weak that they don't impart much resistance to subduction. In fact, you can think of them as a lubricant. They help lubricate the plate interface so that plate velocities can be maximized. By contrast, though, if the interface is sediment poor, therefore occupied by mafic rocks, its viscosity is higher, so plate velocities are significantly slower. So this just highlights the potential importance of the geology, the geological materials that are entering the trench, and the potential for changes in what's supplied to the trench to affect accelerations or decelerations in plate speeds. So everything I showed you on the last few slides is referring to cases where the slab has not yet subducted into the mantle transition zone, which ranges from 400 to 660 kilometers. But it turns out there are important phase transformations that occur at both 400 and 660 that also can influence subduction rates. The two primary phase transitions are olivine going to wadsleyite at 400 kilometers, and ringwoodite, also a polymorph of olivine, going to bridgmanite and ferropericlase at 660. The 400-kilometer transition is actually an exothermic reaction that serves to make the slab more negatively buoyant, so slabs pretty much always penetrate through, and that will actually slightly increase the slab velocity. The 660-kilometer discontinuity, on the other hand, is endothermic, so it increases the buoyancy of the slab and slows subduction. In some cases, it will even cause the slab to lie down or sort of drape itself onto the 660. Here's an example of subduction zone model as a movie in which I've colored the background according to viscosity. So you can see a viscosity increase is implemented at the 660 kilometer discontinuity. I've also in the model toggled the velocity vectors in white, scaled by magnitude. And this shows the drastic effect that the upper mantle, lower mantle transition zone may have on the subduction velocity. So you can see once the slab starts to interact with that 660 discontinuity, it substantially slows and the velocity slow down relative to when it was freely sinking before reaching that depth. Just to note that although that was just a model on the last slide, it's based on observations made using seismic tomography, which appear to show a wide range of slab behaviors at the 660. Some slabs, such as Indonesia on the lower left, doesn't appear very affected by the 660. It appears to simply penetrate right through. Some, such as Izubanan, appears to be permanently draped at the 660. It doesn't look like it's penetrated through the 660 at all. The Tonga slab on the lower right seems to show a section of the slab that did penetrate through the 660, but also has a section that appears to be draped on the 660 closer to the trench. So it shows changes in penetration behavior through time. So you can imagine that these interactions with the lower mantle also have quite important and time-varying influence on subduction velocities. So the last thing I want to cover in this mini lecture is just to discuss a related parameter that is commonly used to distinguish or predict subduction zone behaviors. And I'll just introduce it here, but it will come up again in most of the following mini lectures on subduction. So subduction zones are often classified by this parameter known as phi, which is the convergence rate times the plate age. Phi has units of length, since convergence velocity is length over time and plate age is time. And large values of phi generally represent old plates moving at fast velocities, and small values of phi generally represent young plates moving at slow velocities. Of course, this is recognizing that there are the additional factors we discussed that affect the plate velocities. And phi is useful because it can be related to several aspects of subduction zones that are important in tectonics, including the subduction zone physiography and geometry, and the thermal structure of subduction zones, which in turn influences metamorphic facies that develop, the dehydration profiles, the arc depth and degree of arc magmatism, and seismicity patterns. Here's what the present day global distribution of phi looks like. Perhaps not too surprisingly, the Eastern Pacific has small values of phi because the subducting plates are younger and slower, whereas the Western Pacific has larger values of phi because that's where the oldest section of the Pacific plate is subducting, and it's subducting rapidly. There's an interesting degree of diversity in the phi value, however, which hints at the variations in what's subducting. Japan, for example, has a region of very low phi on the south side of the island in the Nankai Trough, where the very young, hot Philippines sea plate is subducting. But it also has the Tohoku subduction zone on the east with the very old seafloor and high phi values. We'll talk later about how very different these subductions are, both in terms of morphology, thermal structure, and seismicity. Indonesia is another example of a region with quite variable phi values, in this case varying substantially along strike of the subduction zone. There's the young, hot Banda arc on the far right, leading to low phi values. There are parts of the continental shelf from the Australian continent involved, and there's variable aged younging westward oceanic lithosphere subducting in the Java Trench. So as I mentioned, phi is something we'll return to in subsequent segments, but I just wanted to introduce it here to get you all thinking about it as a potential way of classifying subduction zones. So here's a summary I hope you can take away from this segment. The primary factors that influence subduction plate speeds. We have what drives subduction is the slab negative buoyancy, but that's counteracted by interface dissipation, dissipation into slab bending, dissipation into the surrounding mantle, and also counteracted by interactions with the 660 kilometer discontinuity. And I also introduced a classification scheme used for subduction zones known as the phi parameter, which is simply the convergence velocity times the plate age.